Thank you, Jimmy. And great stuff, Harpreet and Matria as well. Like you guys, are doing amazing work in that area. We're going to do something a little bit different now as we switch over to my stuff. Let me get my screen share going. And we're going to be talking about more on the RAG side of the world. So LLMs over to how you combine them with data and with specific focus on what's called GraphRAG. Actually, I don't want to share. That's what I get for clicking the wrong buttons. Let's get that going. So GraphRAG with what's called a knowledge graph, which is a very particular kind of data modeling approach for information that you want to share with an LLM. Hi, I'm ABK, Andreas Kollegger from Neo4j. Let's get right into it and on your time. In thinking about RAG applications overall, for me, and I think for many people as well, there's really three sources of data you start to think about when you're trying to think about what kinds of questions people ask and how those map to different data that you might have available. And so I'm going to run through that first because I think that helps really frame understanding like what a knowledge graph is and then what these GraphRAG access patterns really end up being. You'll hear people talk about, actually, let me advance here a little bit. There's a lot of talk about like unstructured data. That's where most people start with doing any kind of RAG applications. I like to just simplify that as thinking, okay, there's pure text or pure images or pure media of some kind that you've got, and you actually want to, you've got that privately somewhere, you want to make that available to an LLM. You're not training the LLM at this point, but you want to be able to access that information, the information that's kind of in that space and make that available for natural language queries. This, in kind of the computer science terms, this is always under the umbrella of information retrieval, but this is kind of a particular subset of information retrieval. What you're doing here is really just information search. You're just assuming somewhere in the data set you've got the corpus of data, there's an answer that mirrors what the person has asked. So if you're going to ask a question like, what is Apple's primary business? Because somehow you don't know, you can ask that question. And somewhere in the data you have, hopefully it says Apple's primary business is selling phones or services, whatever they claim it to be. And so that's really information search. On the kind of other extreme of this, and I think about it on a kind of a continuum, there are situations where you have pure data. You don't have a corpus of text or other kind of media, but you already have data in a database that you want to be able to ask questions about. And the kinds of questions you ask here tend to be different. And also the access patterns end up being very different. So the kinds of questions you might ask, again, this is still information retrieval, but it is a bit more of like information query. It's not just, hey, go fetch me this information, but tell me something you've got to actually calculate about this information. And so it may not be possible to provide enough context to an LLM to figure out the answer. You have to actually figure out the answer and then hand it back to the LLM to kind of do the post process of like, okay, present it to the user in Shakespearean prose, let's say, because that's what most people want. So in Shakespearean prose, how many iPhones did Apple sell this quarter is the kind of question you might ask out of a structured query to a database. This ends up being the realm of text to SQL or text to whatever query language you have. For us, the query language in graphs is called Cypher. As of last week, there's now an ISO standard. After 40 years, the next ISO standard for SQL is now, there's a graph query language standard as well, which is pretty marvelous. Rolling forward here, you can imagine, as always happens, and as actually happened in some of your the previous talks this morning, right? You end up being able to blend these techniques. This is always the case, right? You start off like just focusing on one area or some other area, and you realize actually you kind of mix this stuff together, and that's useful also. This naturally occurs in, if you happen to have like a WordPress data site or something like that, where you actually kind of have a mix of a bunch of long form text plus some structured data attached to that. And the kinds of access patterns end up being a blend of, let me do a search, but like maybe I'm going to qualify that search, do some ranking on it based on the structured data I have, or the opposite happens as well. I'm going to go through the structured data and then find the text that's attached to that. So you end up with strategies that kind of blend a little bit of the pure data and the pure text in this mixed text and data realm. So the mixed structured and unstructured, call that semi-structured, whatever you'd like to do. In the data set I'm about to kind of walk through, the kinds of questions that end up being different here are, if you knew that there were a bunch of companies that are impacted by a chip shortage, and you knew that there were, investment portfolios that invested in these companies, it'd be great to be able to ask, okay, there is going to be a chip shortage, whose portfolios are affected? That's reaching into the company's information about like who's at risk from chip shortage, but then kind of spanning back a couple of hops all the way to like, okay, who's made investments into that and who's made the most investments. So if you're watching markets, this is the kind of thing you might want to be able to ask. And it combines doing a search with a data query in one kind of access. When you start combining all this stuff together, this is where GraphRAG kind of emerges and where knowledge graphs as a data structure kind of emerge, just incidentally in the act of like kind of elaborating on the kinds of questions you want to be able to ask and expanding what the data set looks like and what your access patterns look like, your strategies for accessing that. You end up with both of those things. There's the data model itself grows into a combined single model that has both the text and the data mixed together. And then the access patterns also kind of grow from simple, just do the search or just do the text to query language, and then mixing those techniques. We call that a knowledge graph. When you combine all this stuff at once, part of the reason for calling it a knowledge graph is that the data structure, when it's well formed and matches well with an LLM, is very readable. A human can look at it and make sense of it and like read kind of through the graph, like almost sentence-like expressions of information. So that's why we call it a knowledge graph. That ends up being really nice for mapping it to natural language questions in a RAG context. And then again, the access pattern that complements that is called GraphRAG, kind of multiple modes of information retrieval, whether it's search, query, or what we call information discovery. We're kind of combining these things and you don't know necessarily how things are connected. Just reiterating that, I guess, drilling down into a little bit, again, that on the search side, fundamentally, that ends up being people start with vector search. That's the natural place to start. But it's search in general. It could be keyword search, could be geospatial search, could be whatever you can search, do that on the one side. Again, on the far other side, on the pure data, those are just turn your natural language into a query. And in the middle, combining those techniques, you end up either using the combined techniques for doing a ranking of the vector search, or expanding the context of the vector search, or doing the inverse, you've done a graph query or a structured query, and then you're attaching information to it. And you kind of, on either side, you're kind of blending the techniques. To make this a little bit more concrete, the example I'm going to go through, that is my go-to these days, there's this thing called the EDGAR database from the US government that is from the Securities and Exchange Commission. This is public data that is available for any company that is publicly traded. They've got to file with the SEC, like what their business is all about. This is what the Form 10Ks are. If you're a public company, you've got to say, here's what our primary business is, here's the risks to our business, all those kinds of things end up going into this Form 10K. Then there's another set of data that we looked at called the Form 13s, which are from institutional investment companies. So the companies that manage huge portfolios, they've got to file as well and say, here's what we're investing in at this last quarter, what the dollar amount was, number of shares, those kinds of things. So for the Form 13s, we were mostly interested in the structured data part of that, like who's the company that's doing the investing, how much money did they invest? So that's the kind of structured data piece of it. And the Form 10Ks is all the unstructured data. We ended up combining all that together. There's a data modeling strategy that I like to recommend to do the way to think about it, because sometimes when people think about knowledge graphs, if you're familiar with them, it comes along with sometimes a bit of an intimidating notion of like, oh, we've got to build a complete ontology of the world or the domain that we think is true. And the reality is, in practice, that's useful if you need it. And certainly there are domains within which that is important. But for folks who are just kind of getting started into this stuff, start with the smallest possible graph and the smallest part of possible taxonomy or organization of that graph and elaborate over time. Don't worry about trying to anticipate all possible structures up front. Start small and kind of iterate. And the iterative pattern ends up being just create some data, figure out what's interesting about that data, what dimension you actually want to basically index, like if it's a vector search or something else, and then just create some connections, whatever connections seem natural. And as soon as you start to create connections, new patterns of access end up becoming possible, and also new features of the data emerge just by creating those connections. In the simplest terms, this is how everybody starts with RAG. If you take a bunch of text data, the first step usually is split that up, create a bunch of chunks out of that. That's the same with the knowledge graph as well. The simplest possible graph you can create is a graph that has no connections. It is just all the nodes without the edges, still a valid graph. The natural thing to do here with text, though, of course, is to do a text embedding of that. Save that as well. You can store that in a knowledge graph, same as you can with any kind of database these days. Everybody's got some version of vector search capabilities. And because it is a graph, though, the simplest possible obvious thing to connect would be, because you know you've got a sequence of chunks, just turn them into a linked list. And that already gives you some benefits, like being able to do things like context windows. Like you've landed on one chunk, you can at least get the previous chunk, the next chunk, up to as many chunks as you want to very easily, because it's just in a linked list. So it's super convenient. This is the overall kind of flow that you iterate through as you're kind of building up a knowledge graph and then iterating through expanding the questions you're able to answer through a rigorous kind of eval round trip. Me as a really a developer more than a data scientist, like I think about this as being like kind of TDD. It's like test-driven development in computer science land. Eval all the time, figure out what works, what doesn't work, and often it's changing your chunking strategy, but then also sometimes changing like your prompt engineering as well gets involved in this. Having done just the simplest possible graph here of just creating a linked list, this is pretty much what the data model looks like. Chunks connected to the next chunks. They've got some identifiers attached to them. The vector embedding is stored there as well. There's actually two benefits to this, because for enterprise settings, like it's nice to be able to like go through a full RAG and like an LLM generates some kind of response. It is very important for businesses that are relying on this stuff to be able to verify and validate what the response is and like cite sources. And so you can actually, the user hopefully takes the time to validate, okay, here's what the LLM just generated, cool. But then you also have the reference text you can look at directly. And for some settings, people drop the G part of RAG, and that's not really interesting. They actually just want to do the first kind of part of the round trip and actually just present the text, because the text itself is what matters to folks. And they're just using an LLM as kind of a natural language interface rather than for generating content. The natural next kind of step, again, just thinking in sort of incremental terms here, you've got all these chunks, they came from a single document. The natural thing to do is like, okay, let's actually connect it to that document. And this provides yet another opportunity for actually having a different set of questions that are answerable, because as soon as you reconstruct the structure that you started from, and here's just one level of structure from the form to the chunks that we split up there, every chunk gets attached to the form that was a part of, and the form will get attached to the first chunk, so the head of the linked list. And while you're there, it's worth taking the time to generate a summary of all the chunks, because for some questions, you don't want a window of chunks, a single chunk or a window of chunks. You kind of want the summary, because if somebody's asking about that level, the sort of a higher level of abstraction, depending on the domain you're in, that maps much more nicely than the detail. But then again, as I just mentioned, it's important if you take that route, it's even more important the further up you go and the more you're relying on a round trip with an LM to generate stuff. For the end user, it's super important to be able to go drill down to the actual text that was used for the summary text you might have gotten. Quickly, just kind of jumping over to the other side, all the way over to the structured data. This is the Form 13s I mentioned. This is the investments, the very simple data model that emerges here. It's just, we've got a list of, for this company, they invested in X number of shares and Y number of value in this publicly traded company. The manager name here is maybe not the most useful name, because they're not managing the company. It's a management investment firm, but for some, for shortness sake, it's a manager. So this manager owns stock in some company. And this is one of the times where it turns out that vector similarity is not helpful for the access pattern. That if you had just the structured data and you stored it in a knowledge graph, the questions that people tend to ask end up being easier to map to just find me variations of the spelling of the company, either the management firm or the public company. And so you end up with a full text index on the names for either of those, because people usually ask for and sometimes mistype, or don't use the right capitalization, all those kinds of things. But they're interested in, tell me about Apple, tell me about, NetApp or whoever it might be. And so you end up with a full text index instead of a vector search. There's another opportunity here for yet another kind of index, I suppose, that because we know the addresses of these folks, it's useful to be able to do, geospatial indexing as well. And we now basically end up with 3 strategies, just still looking at the data, not getting too clever yet, of you might ask kind of arbitrary questions that are going to be coming from the pure text. But as soon as you've gotten to the structured data, you might be asking questions that are better found through doing a lookup for the company names. And then you can also do things like what companies are near other companies. So what management investment firms have invested in companies that are nearby them, and do analysis based on that. So now you have 3 strategies for actually asking different kinds of questions with the structured and unstructured data. The next step, of course, then is to combine the structured and the unstructured data that these public companies filed these forms. And this is when you get to actually do the full blend of all the different strategies. You can do some vector, you can do geospatial plus vector, all the things kind of apply. And because it's all in a graph, you could also do pattern matching. So you could ask simple questions like, what companies of BlackRock, the investment firm BlackRock, which is based in New York City or something, I think, right? Who have they done the most investments in? You can actually do the pattern match on that from just the manager to the company, and find that information, and then have like a kind of a follow-up question for like, okay, and here's what those companies are really primarily doing. That drills down into the unstructured data. So you get these kind of workflows that people can do when they're doing market analysis, by kind of alternating between arbitrary things you might find in the text versus specific things that they're trying to look for that's really captured best in the structured data. And you combine that with vector search, other index lookups, and then pattern matching. This is the summary slide that I have for like the process for this particular data set, the kind of iterative process I ended up going through, from just the pure data, just the unstructured data, to combining it with the structured data, and then all the elaborations I did for like whether it's vector embeddings, full text, or geospatial that I added. As you do things like working with a company or like working for your own interests, what you're trying to investigate, the kinds of questions that you want to ask that aren't answerable, you end up just elaborating in the same way. You follow the same pattern for like, okay, there's a question I've asked that doesn't map neatly to any of these techniques. Either there's information that's missing or there's relationships that are missing. And you go down the path of doing things like named entity recognition, pulling out interesting topics that the baby companies are in. Something that I skipped over here that I probably should have done is, most of these filings, the companies actually cite other companies. And so it'd be really interesting to actually just do that connection, be like, here's a company that does business with these other companies in some way. Once you add that, you can then also do graph analytics on that, things like centrality queries, so like a page rank effectively. So you end up finding out like who's the most influential company, or the company that other companies depend on the most. You can do those kinds of queries, annotating the graph with that, but then also exposing that through GraphRAG access patterns. This continues on through all the different things you can extract from the data, but then also keeping track of who the particular user is who's asking questions, and fine-tuning things. I'm sorry, it's the wrong word to use with this audience, I'm sure. Refining is maybe the better thing to say. Refining your strategy for how you map a user question to the answers based on what you know about the user. That somebody, 2 different people asking the same question are going to ask it in a different way and mean something different because of their context. So the more you know about the user and their history of asking questions, you bring all that in for actually ranking the data that's available when you get results. And also allowing the user to provide feedback that you also then store in the knowledge graph. Okay, that is my whirlwind tour of GraphRAG and knowledge graph. All the stuff I've shown here is available in some notebooks and Python notebooks that are out on GitHub, that are live notebooks, I should say. So at any given instance, they're all broken or working great, because I keep kind of working with this data, and it changes a little bit. But please feel free to reach out to me if you've got any questions. I'm Andreas, either Andreas.Kollegger at Neo4j or just Andreas at Neo4j.
All right, fantastic. So there is one question in the Q&A, but before we get to that question in the Q&A, there were 2 that ended up in the webinar chat. Looks like my cat wants to get on the show. So I think the first question was from Henry, and I'll try to give you context. I think it was when you were on slide 24. So if you want to bounce back to your slide 24, maybe the question will have context. I'd read it out. The question is, are the chunks connected to each other based on spatial location in the text?
Oh, great question. So not in this part. So in this stage here, all I've done is the sequence of chunks that as they were split up, I just put them into a linked list so that they are sequential, so that you could effectively page through the text directly. So it's not in terms of their internally whether they're similar or not. Although that's something that we in other contexts have also ended up doing. So you end up with clusters of chunks that point to each other.
Cool. And I think the next question that was in the webinar chat that that was asked around slide 21 or 22 in the create, enhance, connect form 10K slide, I think. I don't know
Yep.
if there's enough context here with this question, but the question was how you save that separate or within the nodes. I don't know if that's helpful.
Um, Oh, maybe it's got to do with like chunking strategy. I'm going to guess, and let me know in the comments if I'm headed down the wrong direction. But that even at this stage, this is if that's the question, I think it's a great question. Chunking is hard to do well. Um, Folks start down the path of chunking because of context windows, and they're trying to get like just enough text to be appropriate for the question and passing that through. As context windows have grown, the different criteria actually ends up being finding the right size chunks that are most likely to mirror the question that is asked. Because sometimes you'll get actually the information is appropriate or best found in a chunk that doesn't have highest similarity score if you've got chunks that are too big. And it all depends on like what the embedding strategy is as well. I guess what you're using for embeddings. So it's highly sensitive to like what you're using for the embeddings and then what the actual text is for like what your chunking strategy ends up being. But the fundamental driver ends up like trying to mirror what the questions are that you're anticipating. So there's a lot of art involved in all of that.
All right, so I think that your ability to have an intuition about what the question was based on your on the question itself was pretty good because I think we had the follow up in the webinar. Try it was during the embedding. Do you put the embeddings in the nodes that are chunked or do they stay separate? It sounds like you were close.
Yeah, yeah, that's right. So the embeddings and the text itself get stored in the chunks. So the chunks end up being data records basically in the database, and the vector embedding itself is just an array of floats that is backed by an index that is able to do vector similarity search. So cosine similarity is the typical thing we use.
Okay, awesome. Then I think we can bounce finally down into the Q&A queue. And I think the first question is actually just looking to connect with you over some topics. So maybe we can take that one offline. But the next two definitely are questions worth looking at.
Okay, so let me bounce over to that.
If you want, I could just read them to you. The first question is, should semantic chunks help the size of chunks? Can we give per node in Neo4j? Should semantic chunks help the size of chunks? Can we give per node in Neo4j?
So this is back, I think, around the same topic of like chunking strategies, and it is highly dependent on your domain. There's no perfect answer here. For example, like for some of our enterprises that deal with that are doing this stuff right now, they have a lot of information that they use from legislation, where basically what they really want is like in the very structured, unstructured data, like for subsection 3.25, they want that to be a chunk, whether it is a single sentence or two paragraphs, right? So it ends up being very dependent on your domain. The domain might have enough hints about the chunk size that you want that to determine what's going on rather than arbitrary character length or give me two paragraphs or one sentence, in other domains. So it's very domain dependent.
All right, and then our last question is actually a 2-for-1. So it's a two-parter. Could you tell me about the management graph of updates? And then second, what is the security of the graph method?
Okay, interesting. So I'm going to answer those in reverse order because the second is easy. You get to apply security rules to the graph access rules. So you have role-based access control over the graph itself. And so if you do know the user who's asking the question and you have some role-based access control over that, then that also constrains what they're able to see. That is either happens as kind of a post process. If you're doing a vector search, it doesn't apply into the vector search, But like when you then tie in the vector search with the nodes that are result, that's when the visibility ends up hitting. So you still search for stuff, but then it won't be visible to the end user if they're not allowed to see that part of the graph. And definitely on the pure data side, all those things apply directly for what they can actually perform in terms of queries. A lot of interesting actually subsects of that I want to get into. And I've forgotten the first part of the question. Which one
Oh,
was it?
so the other part was how do you manage updates? Management of the graph updates.
Yeah, so it's all the techniques you're used to for managing any kind of database updates basically apply here. One of the small advantages, I guess, of being a graph is that you can sometimes updates means if you're doing like data migrations and things, there usually aren't data migrations involved in graph structures. Like as I was talking through kind of evolving the graph, that's not a migration every time. You're just kind of accumulating stuff. You don't have to pre-decide all of the structure first. You just add structure as you would like to, and that's really nice. But for doing data, adding data, it's just upserts. So if you already have data, you just do an upsert basically.
All right, and we have one last question that snuck in, and we're gonna take it anyway. How do you do the index search or pattern matching after you get the required chunks using distance-based similarity search?
Right. So that ends up basically being brute force. So if you do a pattern match first, typically that ends up constraining the number of chunks that you hit. And if you're hitting less than, probably even like up to like 10,000 or something, like it's as fast to just do the calculation yourself. So like in the queries, in the Cypher query that you can write, you do a pattern match and then you kind of do a post process of that. Where you're just actually going through all the nodes and just calculating the coastline yourself rather than doing an index lookup for it. Because it's small enough batches that the pattern matching has reduced the size overall that's not impactful.